So thanks for coming to this seminar during finals week, and a couple folks are online. I just wanted to let everybody know that Matt is an undergraduate student, which is pretty unusual to have any form of a seminar for an undergraduate student. So thanks, Matt, for having the courage to do this. That is a big deal. Matt has been working with Tyler and I under the VORTEX Southeast USA PERiLS funding mechanism, finishing some of the work that Tyler Pardun started when he was an undergraduate working with us. And Tyler has worked in some of his quote unquote free time while he's been a graduate student on a different project. And so we hired on Matt to work alongside Tyler with finishing some of that work. So what we'll see are the fruits of some of that labor over the past 3 to 4 years since Tyler was undergraduate and now Matt. There's some pretty cool stuff in here. So we're just really excited to kind of have a showcase of the work of students over time. So with that, take it away.
Cool. Thanks, Liz. Well, I was going to explain what I've been doing, but Liz already did that. So, so with my time here, I've been doing a lot of case studies, looking at clamps data in VORTEX Southeast and PERiLS, and using that data to explore the atmospheric boundary layer and how it evolves and behaves in the presence of convection. And for those of you who don't know what clamps is, I don't have that's on my computer. Okay. CLAMPS stands for Collaborative Lower Atmospheric Mobile Profiling System. And it does pretty much what it sounds like. CLAMPS is equipped with a few instruments, a Doppler lidar, microwave radiometer, and an interferometer. And these 3 instruments combine to derive vertical profiles of the atmospheric boundary layer. You could look at UV and W wind components, as well as thermodynamic variables like temperature, dew point, all kinds of other things. And so what CLAMPS allows us to do is basically take these high temporal resolution soundings of the lowest couple kilometers of the boundary layer. And so it allows us to look at the structure and behavior of a lot of different features and how they evolve. And we could use that to optimize real-time forecasting. And while that's not the main focus of this talk, I wanted to discuss this case study, one of the few that I did, to just kind of highlight the power that CLAMPS has in terms of real-time forecasting, to understand the boundary layer. So this case here, April 22nd, 2017, this was during VORTEX Southeast. There was a slight risk this day, only a 2% for tornadoes, so it wasn't really expected to be a tornadic day. The main threat was associated with damaging winds due to this big MCS here across southern Tennessee. And during this case, CLAMPS 2 was located in Scottsboro, Alabama, which is far northeast Alabama. It's where that red star is there. And so we were able to use later on, which I'll show, use CLAMPS to kind of profile how the behavior of this outflow boundary and supercell that ended up producing a tornado evolved. So as you can see here, this is a couple hours before it crossed over CLAMPS. We've got that big MCS. You can see that outflow boundary starting to be released. It ends up propagating down to the southeast. And you see kind of a supercell structure on the west end of it that's a little more separate from the main system. So if we look about half an hour later, we still see that outflow boundary starting to progress southeast, and that supercell structure has become a little more discrete, starting to intensify. And if you notice, the outflow boundary and the supercell are connected pretty closely. So it almost appears as if this outflow boundary is pushing this storm out and away from the main MCS. So if you continue to go forward, this is about an hour later. The supercell is still there. It's kind of in some weak stratiform precipitation, but the main bulk convection related to the MCS has kind of diffused and moved off to the east. And you can't see the outflow boundary quite as well in this, but if you look at kind of the heterogeneity of the reflectivity and those new cells that are kind of initiating out ahead of it, you can infer the position of the outflow boundary, which is still tied really closely with that supercell. So it's appearing as if there's some sort of connection between this supercell and this outflow boundary that allowed it to end up producing a tornado. This was 15 minutes after that last scan. And at this point, there's an EF1 tornado on the ground. And this was only about 15 miles or kilometers northwest of CLAMPS. So if this ended up continuing southeast, So it passed over clamps, and I was able to look at the clamps data to see kind of the properties of this outflow boundary and what effects it had on the boundary layer and how that could possibly provide insight into why it produced a tornado. So this here, oh shoot, that was one behind down here. So the top figure there, that is the temporal evolution of vertical motion in the lowest 1 kilometer of the boundary layer leading up to the arrival of the boundary. So the boundary arrives right at the interface between that dark red and dark blue, which shows this boundary is causing some pretty significant ascent, about 2 to 3 meters per second, across throughout the lowest kilometer of the boundary layer. But before, and it's followed by some equally strong ascent immediately after. But before that, it's pretty quiet, a little bit of sinking motion going on, nothing too crazy. But I also overlaid the wind bars here, which is horizontal wind speed and direction. And what you'll notice is way out in advance. So at the very beginning of the plot, it's about 2 hours, or I guess about an hour and a half before the arrival of the boundary, you have a pretty homogeneous southwesterly profile. It's all southwesterly winds. But as you start getting closer to the arrival of that boundary, some of those winds, especially near the surface, start to back and become more southerly and southeasterly. So you can infer that this boundary, the ascent that it's causing, is causing that surface convergence that's allowing a backing of winds in advance of it. And this should increase low-level vertical shear, which should in turn improve the storm's chance of producing a tornado. And I was able to quantify that by this graph down here is what clamps measured of 0 to 1 kilometer storm relative helicity, and that's the blue line. And as you can see, leading up to the arrival of the boundary, which is that dotted line there, that second dotted line, you see 0 to 1 kilometer storm relative helicity increase leading up to it. So that shows, that reflects kind of what the backing of the wind is doing in the boundary layer. It's increasing that low vertical shear. Additionally, if you look at that red line, that is what the meso-analysis estimated 0 to 1 kilometer storm relative helicity to be. So clamps observed a lot stronger low-level vertical shear than what meso-analysis had indicated. And additionally, if you look at the more long-term evolution of this, so this is a full 12 hours before the arrival of the boundary, there's a lot more ebbs and flows and peaks and valleys in the magnitude of storm relative helicity as measured by clamps than as suggested by the meso-analysis. So this suggests that low-level shear is very sensitive to just small atmospheric boundary layer processes that our current observational or our modern observational techniques are just don't capture as well as they could, as well as clamps did here. So this kind of just shows the power of using clamps real-time forecasting. For example, if we had clamps located where that red star is, so in southern Tennessee, we would have been able to profile and observe the properties of this outflow boundary a lot earlier. So a real-time forecaster would have seen this, the same figure that I showed in the last slide, and they would have thought, okay, well, this outflow boundary is causing ascent, so that could enhance the updraft of the supercell as well as initiate new convection, and it's increasing the low-level vertical shear. So with that in mind, as long as that outflow boundary stayed tied to the supercell, you could say that along that shaded corridor, there should be enhanced tornado potential going forward. And that would have provided a lot more lead time for that tornado if we had a clamps up there in that location to really gain insight into what was going on with this boundary supercell interaction. And so this case was really interesting. Again, it really shows the power of clamps, how it can be used to capture these high temporal resolution observations and how they could improve real-time forecasting. And so I did a couple other case studies on this, but this one in particular made me want to look at other times where a tornado came into close proximity to clamps, because we could look even more into this, gain more insights. And so to do that, I looked at the NOAA damage assessment toolkit, to see all of the tornado paths from 2017 to 2022, the time where clamps was deployed down there, just to see if there were any other times where a tornado was close by where we could do a similar case study. And when I looked at this, I almost immediately changed my focus because I noticed a very pronounced bullseye of tornado paths there in southern Mississippi. They're a lot more dense and concentrated than all the surrounding areas. And there's a very sharp gradient between areas of very sparse tornado paths and very densely concentrated tornado paths. So it made me wonder, is there some sort of feature here that makes this particular region more susceptible than the surrounding areas? So I looked at topography, and this was what I found. And I had no idea this existed, but on the eastern boundary of the Mississippi River Delta, there's a very sharp terrain gradient. It goes from completely flat, not much vegetation, to a lot more rugged terrain. And it's not a super substantial increase in elevation, but it is a very noticeable difference in terrain that shifts in a very small spatial scale. So overlaid, the dense area of tornado reports almost directly overlays just the downstream area of that ridge. And I also made a heat map of that just to kind of show that bullseye. That's just the amount of observed tornado paths per kilometer. And so it made me wonder if this terrain feature has any effects on the atmospheric boundary layer that could influence the tornado genesis process. So that was kind of the research question that I had going forward, switch focus a little bit. And so my original hypothesis with this is something like the schematic diagram over here. There's the ridge in that dark black line, and you have a ambient field of horizontal vorticity. And then as a storm approaches, and it has westerlies behind it with some sort of boundary or bore or something of that nature, once that bore reaches the terrain, the ridge, it causes orographic ascent that increases the vertical motion going into the storm updraft, and two, is able to dynamically tilt the ambient vorticity, which could then aid in the formation of a mesocyclone and produce tornadoes as it traverses the gradient. So I thought, okay, this is a good hypothesis, but in order to prove this, I need to see if this terrain feature is even capable of producing orographically induced ascent, because it's not necessarily the Rocky Mountains. The Rocky Mountains can produce ascent, but this feature is not the Rocky Mountains. It's a lot smaller. It's a lot more or less prominent. So to do this, it was convenient. For PERiLS 2022, we had both clamps 1 and clamps 2 deployed out in this region. Clamps 1 was out in the middle of the Mississippi River Delta, Lake Village, Arkansas. It's flat. You could tell at the bottom there's not a lot of vegetation, whereas clamps 2 was conveniently located in just north of Yazoo City, Mississippi, which is right on that terrain feature, right on that gradient, that boundary. So to the west, it's pretty flat, pretty sparse vegetation, where just to the east of clamps 2, there's a lot more rugged, elevated terrain with a lot more vegetation. So next I wanted to, in order to kind of assess my original hypothesis of whether or not this feature could induce orographic vertical motion, I wanted to visualize the relationship between horizontal wind and vertical motion as detected by clamps. So before I kind of get into the results of that, I just wanted to provide a brief example of how I visualized this. So I used a wind compass. So for example, this point right here, this blue point, this would represent horizontal wind out of the northeast with a corresponding descent as measured by clamps. And similarly, this point would represent horizontal wind out of the west, and the red would indicate ascent, so rising motion as indicated by clamps. So what I did next is I took every single 5-minute period while clamps was deployed out here, which was a couple of months. And I made the same plot for every single one of those 5-minute periods. And I came up with that top figure there. And that's kind of a mess, but what it led to was this bottom figure. So what I did is I went through each 2-degree interval across that wind compass, and I averaged for every time the wind was in one of those 2 degrees, what the mean vertical motion was. And that's what that bottom plot shows. And so that interior black circle is 0. So that's no mean ascent or descent. Well, everything outside of that is ascent and everything inside of that is descent. And I also put the angle of the terrain, and I just kind of inferred that by placing a compass right on top of the picture. And what you can see is any wind coming from the west of the terrain gradient, which would be upslope, actually produced mean positive vertical motion, so rising motion. Whereas most everything that came from the east of that terrain gradient, so downsloping motion, was a mean negative vertical motion, so descent. So this proved that there is indeed some orographic effect here that is capable of influencing vertical motion. So, and just to further set this in stone, I wanted to compare this and do the same thing with clamps 1, which was not located next to the terrain. It was out in the middle of the Mississippi River Delta, to make sure it wasn't like a synoptically driven relationship, because they were close enough to the point where they'd be similarly affected by synoptic setups. And that resulted in this figure here, with the red line being clamps 2, so the one with the terrain gradient, the blue line clamps 1, and then the red shading the difference between the two. And if you look closely at that blue line, there's really no noticeable correlation between the direction of the horizontal wind and the magnitude or direction of vertical motion. It all just kind of fluctuates right around the 0 mark. And clamps 2, there's a lot more ascent than clamps 1 with upslope flow, and a lot more descent with downslope flow. So this further proved that, okay, this feature does at least have some impact on vertical motion due to orographic effects. So this was every 5-minute period during this time, whether it was convection, no convection, day, night, every 5-minute period. So in order to narrow it down and focus more on the features that I outlined in my hypothesis, I wanted to look exclusively at the pre-convective boundary layer. So this was before the arrival of convection. So what I did is I looked at cases where convection passed over the clamp sites, both clamps 1 and clamps 2. And during this time, I was able to identify 9 cases where convection passed over. And for the purpose of this, I did a very subjective identification. So if it was just a little rain shower, I didn't count it. It had to be some notable deep convection. And then I did the same thing as before. I looked at the relationship between wind direction and vertical motion, but only 2 hours prior to the arrival of convection, to see how the convection affects this relationship. And what I ended up with is this. So the left here is Lake Village, is the one in the Mississippi River Delta where it's flat. And you see pre-convection, it's dominated almost always by a southerly flow. There's a little bit of mix, but ascent is more dominant, and it's all condensed in a pretty small area. So that's pretty much anticipated. But if you look at Yazoo City, which is the one on the right, it was actually the exact opposite of what I first expected. What I expected to see when I did this is to see most of those dots coming out of the west, and most of them being red to indicate that upslope motion to kind of go along with my original hypothesis. But it's quite the opposite. It's dominated by actually southeasterly to easterly flow pre-convection, and that indicates, as you would expect, downslope or descent. So I thought that was really interesting. So I wanted to gain a little bit more insight into the structure of the boundary layer as a whole. So I created these composites here. And once again, same thing. On the left, it's Lake Village. Pretty subtle ascent leading up to convection, not much crazy. Whereas on the right, Yazoo City, it's actually, all those blues indicate descent as the dominant form of vertical motion within the 2 hours leading up to convection. And if you look closely at the wind direction, you see a lot of backing throughout this entire period at Yazoo City. Where if you look at the Lake Village composite, everything's pretty much directly out of the south during that whole period. But this backing flow it would be downslope. It would be down the slope, causing a descent, as this shows. But backing surface flow is very important for the tornado genesis process because it makes that vorticity more streamwise. So that led me to, I looked at some literature and kind of thought about it on my own, and I came up with a new hypothesis, which is this right here. So this has the same kind of initial conditions where you have a storm approaching the terrain feature, you have that ambient horizontal vorticity, but this time I consider the effects of the storm inflow and just the vertical, those red arrows are just the vertical motion that's induced by solar heating and just the overall synoptic ascent, so that warm air advection. And it's pretty uniform out ahead of this convection. But when the convection starts to approach that terrain gradient, that inflow wind, it goes downslope because it goes towards the storm, so it's going downslope, and that causes the descending motion that's terrain induced. And that ends up suppressing the background ascent that I talked about before with the synoptic environment and solar heating to create a horizontal vertical motion gradient. So you have descent just on the lee side of that, the ridge, whereas you have ascent getting closer to the storm. And this horizontal vertical motion gradient, then theoretically, my hypothesis is that it tilts. That's the tilting feature of the ambient vorticity. So it gets tilted into the updraft and promotes the development of a mesocyclone. And another thing I considered here was that with these background synoptic conditions and with the flow the way it is usually in a severe weather environment, you should have this process occurring pretty much relentlessly. So it made me wonder if you have that sinking motion on the lee side of the ridge, you have that rising motion. And another thing to look into too, to think about here, is that when you have descent, terrain-induced descent, you get drying. So it would lead to less buoyant air as opposed to the more buoyant air further west. And this would just generate baroclinicity in this environment. So it made me wonder, is there some sort of quasi-permanent corridor of orographically induced horizontal vorticity just right along this terrain gradient? So this next slide here, this is where it really tied it all together. I made composite photographs of the different environments. And I also included Scottsboro. I also found 9 cases of convection arriving there and did the same 2-hour composite process. And Scottsboro was from the case that we talked about at the very beginning. And I made composite holographs. And if you look at the Scottsboro and Lake Village, which is in the middle, the holographs, yes, they're favorable holographs for severe weather, but they're pretty much straight in the lowest 0.5 kilometers. Whereas Yazoo City, there's substantially more curvature right near the surface in the lowest 0.5 kilometers. So that would promote more streamwise vorticity. And that's due to that backing winds from the effects that we talked about previously. And additionally, this is just another thing I noticed. I don't know, it probably doesn't have relation to the terrain gradient, but another thing to notice. So these 2 different photographs on each, the dotted line is 2 hours before the arrival of convection, whereas the solid line is only 15 minutes. At Scottsboro and Lake Village, there's very little change in the 0 to 1 kilometer shear vector. That's pretty much the same. Whereas in Yazoo City, there's a substantial acceleration of that 0 to 1 kilometer shear vector. So I just thought that was kind of another interesting thing to point out. Could also have impacts on increasing that storm relative helicity. And then just to kind of quantify these photographs numerically, I looked at the evolution of the actual values of 0 to 1 kilometer storm relative helicity leading up to the arrival of convection. So these are the same composites. The blue line is Scottsboro, the red line is Lake Village, and the green line is Yazoo City. And if you notice, they all kind of fluctuate differently for most of this time. But about 30 minutes before the arrival of convection, you start to notice that the Scottsboro and Lake Village sites, the 0 to 1 kilometer storm relative helicity as measured by clamps, trends downwards. Whereas at Yazoo City, it actually trends upwards, leading to, at the arrival of convection, the storm relative felicity over Yazoo City is up to double of what it is at the other two sites, substantially higher. And that's, again, due to the terrain-induced backing of the surface level winds that makes that vorticity more streamwise. So while this is very interesting research, there's definitely some limitations to this. And the biggest one, of course, is the clamps were only in these locations for a few months during PERiLS. So I was only able to identify 9 cases of convection. And this kind of just limits the accuracy because one really different case could have pretty substantial effects on the overall composites. But if we were to have clamps out in these same locations for longer, we could get more cases and get more accurate composites. And then additionally, I didn't consider horizontal wind speed with these composites, with the relationship between horizontal wind and vertical motion. I only looked at direction. So that's another thing to consider that could potentially lead to different differences in the results. And then another big thing is when I looked at the horizontal wind, I looked at the mean of the lowest kilometer. And I did this because clamps has a hard time resolving the near surface environment. It's very volatile. It's not quite as accurate. So if I only looked at that, it would just kind of blur the results and it would be hard to see this relationship. So I used the lowest 1 kilometer to kind of get more consistency, but it's important to consider that the peak of that ridge, the highest point, is only about 200 meters above the low terrain to the west. And so obviously flow at 1 kilometer won't have substantial impacts. It won't be substantially impacted by the terrain. So that's just another thing to consider. It would be good to have more high resolution data of just the lowest little bit, which we could potentially use copter sons for. And then additionally, I talked about it briefly before, thermodynamic variables. If we were to look into how thermodynamics are affected by the orographically induced vertical motion, that would provide more insight into what's going on here. And then finally, the next step, which I'm going to do, which we talked about doing next, is normalizing these composites with non-convective cases. So looking at cases where there was no convection and producing these same composites just to see just to kind of look more into what's directly terrain induced and what relies on the presence of convection and how that kind of plays into this whole relationship. But overall, despite these limitations, this was really fun research to do, gained a lot of insight. And here's some of the literature that I used for developing the hypotheses. And then other than that, that's it. Thanks so much for coming.
So I would like to open the floor to questions. So if anybody has any questions for Matt, feel free to ask them. You can also accept questions via the chat. If anybody has questions in the chat.
Oh.
Yeah, very nice. Nice.
Thank you.
I'm solving the hypothesis. My question would be a very basic one. You showed qualitatively that your hypothesis makes sense.
Mhm.
How do you get to quantitative?
Yeah, I mean, so I didn't really talk about it, but I include some quantitative results here with the exact magnitudes of the vertical motion at different wind directions. But other than that, I haven't really gotten into the depths of the quantitative stuff yet. I would like to, I guess also with the storm relative felicity evolution at the end, that quantifies things a little bit. But there's still a lot to look into in terms of the quantitative aspects of it. Like, again, looking at how exactly the ambient vorticity is and how that changes numerically in relation to these features. And also looking at numerically at like the thermodynamic variables is another thing I want to do. So yes, qualitatively, I have a lot here, but I definitely need to do more quantitatively.
In the line of look at what's the magnitude of the downdraft in the absence of the
For sure.
see whether how much that in downdraft will enhance this when you have the approach. Something like that would be
Yeah, no, I think that's a great idea. Thanks for the suggestion. Very nice.
Well, with that, I think we can thank Tyler. Sorry.
Thanks, Tyler.
And I'm excited to see what else you produce and where we go from here. Thank you.